Hello, so this is a revision video for APChemistry 2.2, Intramolecular Force and Potential Energy. This is a revision video, meaning very few explanations are given, we just cover the exact material that you need to know for this module. For full videos and lessons, please check the links in the description below. When two atoms form a covalent bond, there is electrostatic attraction between the positively charged nuclei and the shared electron pair. However, there is also repulsion between the positively charged nuclei themselves. As a result, the atoms will arrange themselves to give a bond length that maximizes attraction whilst minimizing repulsion, the most stable arrangement. Bond length is described as the distance between the center of each nucleus. This internuclear distance determines bond strength and bond length. A potential energy versus internuclear distance graph just shows how the energy of two atoms changes as they form a bond. As the atoms move closer, initially attractive forces dominate, lowering the potential energy. In other words, the electrons get attracted to the positively charged nuclei of each atom, and this attraction lowers the combined energy of the two atoms. At a certain distance, the energy reaches a minimum, and this is the bond length. If the two atoms get any closer than this to each other, now repulsive forces between the two nuclei cause their combined energy to increase rapidly. Such a graph can show us the bond energy, the energy required to separate the bonded atoms. It corresponds to the depth of the well from the zero potential energy line to the bonded atoms together. Bond order refers to the number of electron pairs shared between two atoms. A single bond has one shared electron pair and a bond order of 1. A double bond has two shared electron pairs and a bond order of 2. A triple bond has 3 shared electron pairs and therefore a bond order of 3. As bond order increases, bond length decreases and bond strength increases. This is because more shared electrons lead to greater electrostatic attraction between the negatively charged electrons and both nuclei. This stronger attraction brings the nuclei closer together, given a shorter bond, and requires more energy to break, meaning the bond is stronger. For example, carbon-carbon single bonds are longer and weaker than carbon-carbon double bonds, which are also longer and weaker than carbon-carbon triple bonds. It isn't just the bond order that affects bond length. Atomic size also does. Larger atoms form longer bonds because their outer electrons are further from the nucleus. When considering the strength of bonding in ionic compounds, it's slightly different because we don't have individual bonds. Instead, we just have electrostatic attraction between oppositely charged ions in all directions. The strength of this attraction or interaction can be explained by Coulomb's law, where the force of attraction is proportional to the charge of particle 1 times charge of particle 2 divided by the distance between the particles squared. And the distance between the particles here is given as the distance between the nuclei of oppositely charged ions. Coulomb's law shows us that in an ionic compound, the greater the charges of the ions, the stronger the attraction between them. And the smaller the ions, so the smaller the ionic radii, the stronger the attraction between them as well. This helps explain why lattice energy in ionic solids increases with higher charges and smaller ions, but that's covered in more detail a little bit later in the course. Exam tip here. When comparing bonding strength in ionic compounds, we use Coulomb's law. And when comparing bond strength for covalent bonds, we use internuclear distance and the potential energy graphs previously shown.